Yeah, good afternoon, everybody. So my presentation today is just to speak a little bit of what are the opportunities regarding waste heat recovery in terms of energy efficiency within industry. So my presentation will include a background to heat and energy usage within South African industries. I will cover an overview just at a high level of some of the heat source opportunities that are available. I'll provide a very brief introduction to some heat recovery technologies. It should be noted that this really won't be a comprehensive review, otherwise you'd be here all afternoon. And then I'll provide two short case studies that just show the benefits of where heat recovery has actually been employed in South African companies. And then I'll just provide a short overview of some of the thermal energy research that we're going to be doing at the Energy Centre. So just a short overview of how energy is broken down within our economy. We could see that as of 2015, the IEA energy balances show that industry is sitting at about 37% of final energy consumption. So industry is still currently the largest consumer of energy. And then when we look in terms of consumption of electricity, final electricity consumption is sitting at 61% by industry. How is that energy broken down amongst the different sectors of industry? So what we can see is the shift in energy consumption between 2005 and 2015. Again, iron and steel is the largest consumer of energy, followed by mining, chemical and petrochemical, and then non-metallic minerals, which is really the cement manufacturers. What we can see is an increase, unfortunately, in the non-specified industries, according to the Department of Energy. So we don't have a very clear breakdown of that 38%, but it really shows that most of the energy consumption is still sitting in the energy-intensive sectors, where there are significant opportunities for waste heat recovery. When we look at where does that energy go within typical industrial processes, the DOE really estimates that about 2/3 of the energy end use within the industrial sector is for process heating. There's also some process cooling, as well as hot water requirements and HVAC. So really, when we look at the end use of energy, more than 70% of that energy is thermal in nature. When we look at the breakdown of energy consumption and what are the energy carriers, only 37% of industry energy consumption is electricity. So there's a lot of focus on electricity and decarbonizing the electricity sector and energy efficiency measures around electrical systems. But really, if we only focus on electricity, we're missing a large piece of the puzzle. And what we need to do is look at ways we can reduce the direct consumption of fossil fuels, so coal, oil and gas within industry, and waste heat recovery is really a significant opportunity for this. Some graphs that we'll all be very aware of are rapidly rising energy prices. I think we all know that Eskom tariffs have increased significantly in nominal terms. So the actual price that we pay, it's between 2005 and 2019, it's gone up by 430%. In real terms, which is really what we look at in the energy space, if we remove the effects of inflation, that is about 150% increase. In terms of diesel prices for industry, in real terms, it's actually been reasonably flat, but it can be subject to high volatility. So that makes it very challenging for industries to plan their costs ahead when there can be these massive spikes in energy prices. David already alluded to it. Coal prices have been steadily increasing. When we look at this graph, it's difficult, unfortunately, for us to get detailed data on coal costs because most of the contracts with many companies are confidential, and it also depends strongly on how far the company is located from the mine. But reasonably in Gauteng, we are now seeing companies that are paying in the order of 1,000 to 1,500 rand per ton of coal. So the coal prices are increasing steadily as well. So this really presents a new opportunity for waste heat recovery. When a lot of heavy industry was built in South Africa, it was built at a time when historically we had very low energy prices, so very low cost coal and electricity. So in many cases, a lot of infrastructure was installed in plants where it wouldn't have been an economic alternative. It just made more sense to either burn more coal or use more electricity. The US Department of Energy really estimates that between 20 and 50% of the energy input to industrial processes is actually discarded in some form of waste heat. So really, waste heat is one of the highest potential opportunities for energy recovery. And I think at the moment, it doesn't really get the spotlight that it deserves. If we are focusing on energy efficient lighting, but there's a furnace next door that is spewing megawatts of energy in terms of waste heat, it really is a significant opportunity. So what are some of the factors that we consider when we look at opportunities for waste heat recovery? Well, the first is really heat quantity. How much heat is available? What can we use in another process? But then we have to look at something called heat quality, and the engineers in the room will be familiar with the concept of exergy, but really what we're looking at is the temperature level of that heat that is available. The closer that temperature is to ambient, the less useful that energy becomes to us. So really, industries that have the highest exhaust gas temperatures are well suited for waste heat recovery, and typically you will see that in large furnaces and foundries and things like that, where there already are some existing heat recovery solutions. Other questions are, what is the working fluid? Is it gas? Is it liquid? How is that energy carried out of the process? Is it hot material that has been cast that is leaving the process? There are many things to consider, as well as things that are minimal allowable working temperatures. So that considers in flue gas, if you look at the acid dew point and corrosion issues, if you drop below that temperature. And then finally, this is quite a really important one, is looking at operational schedules. So especially in batch-wise processes, it can be really technically challenging to recover that waste heat and use it in a consistent manner into other processes, especially when the operational schedules aren't aligned. So a typical waste heat recovery process will really include the heat source. So there you're talking about combustion exhausts, process gas exhausts, hot gases from furnaces and ovens, or even cooling tower water. Then you move to the heat recovery equipment, where we're looking at regenerators, recuperators, flue gas economizers, waste heat boilers, and some thermoelectric generators. Then an optional addition to a waste heat recovery system is thermal energy storage, which is really the background that I come from. There we're looking at sensible, latent, and thermochemical heat storage. And then finally, the end use. What are we going to use that heat for? We can use it for preheating, so in an economizer, preheating the feed water going into the boiler. We can use it for hot water supply within a factory, electricity generation, or space heating. Those are really some of the options. So if we're concerned about what is the temperature involved in the process, if we look at a high-level overview of different industrial sectors that might have a high potential for waste heat recovery, we can immediately see that the energy-intensive sectors of iron and steel, non-ferrous metals, mining, chemicals, all of these sectors have high-temperature processes. And what we are really saying as an energy center is we need to do some deep dives into these energy-intensive sectors to really see how much heat recovery are they doing at the moment. How much heat recovery was installed when a lot of that infrastructure was first put on the ground. If you look at, then again, what are some typical exhaust gas temperatures from these kinds of processes? So really in the iron and steel making, you have temperatures approaching 1,500 degrees. So they have a significant potential. And then moving down in terms of ceramic manufacturers, and then all the way down to cooling water from like furnace doors and things like that. And one of the technologies that we are actually investigating as the Energy Center at the moment is something called an absorption heat transformer, where we are actually looking at taking low-grade heat sources and seeing if we can raise their temperature so they can become more useful above 100 degrees Celsius within processes. In terms of heat recovery technologies that could be available to various industrial processes, on the passive side, we're looking really at your typical heat exchangers. but then also thermal energy storage, and I'll talk a little bit more about what regenerators look like. On the active side, you're looking at what can you do with that heat, transform it into a different energy carrier. So on waste heat to power, you have your typical steam cycle for Rankine cycle, then also organic Rankine cycle and the Klein cycle. So the organic Rankine cycle really allows you to have a higher efficiency and lower capital cost for smaller steam systems, smaller systems, because it uses really a refrigerant. So it has a high efficiency at low temperatures. On waste heat to cold, what you're talking about there is an absorption chiller where you can use heat as an input and get cold as the output or cooling. And then waste heat to heat, we're really talking about how can we upgrade those sources through heat pumps. So I'll just flick very quickly through some technologies that are available. So a recuperator, here we're talking about a constant recovery of heat from a waste stream. This is an example, I think, of a radiative recuperator on an exhaust gas system. So these systems are really suited to high temperature furnaces, combustion, where you can do some typically preheating of air going into that process. Another option is a technology called regenerators. So a regenerator actually involves a small thermal storage unit. So what happens is on the one side of you typically have two beds that are either ceramic bricks or honeycomb monoliths. And from the exhaust gas, what you do is you recover the heat on the one side, and on the other side, you preheat the incoming combustion air. Once the two beds once one is fully charged and the other is fully cooled, then you reverse the process, and that way you can recover a high amount of energy. These are typically used when you have quite a dirty exhaust gas that is available. Other more niche technologies, you get rotating heat wheels. So this is really a porous medium that is cycling between two ducts. One of the advantages of this technology is you can really, in many HVAC type applications, you can also recover moisture from an airstream. They're typically limited to medium temperature applications, so sort of below 300 degrees. Sealing and expansion issues can be a problem, and you also get some cross-contamination between gases. You can also look at a waste heat boiler. So here you could look at generating excess process steam that could go back into your process, or you could use that steam or another working fluid to drive electricity producing cycle. So, and this isn't really even scraping the surface of different heat exchangers and passive recovery techniques that are available. It's really a case of how can you match the technologies that are available off the shelf today commercially to specific applications, but then also, as I'll talk in a case study just now, of how can we do R&D, and specifically what we're looking at the Energy Centre is how can we identify new opportunities and new technologies that can be deployed in the waste heat recovery space. So this is a first case study. It's from the project developer on this was CSIR Energy. The project was conducted at Anglo American Platinum at their Waterfall complex at the smelter. So as part of their, I think it's called the ACP plant, essentially what's required is that the off gases produce excess heat within the process, and to keep the converting process at a specific temperature, they initially actually had a fan air cooling system. So they were actively just cooling their process down and dumping that heat into the environment. So what CSIR Energy did was they went to them and they said, let's do something useful with this heat supply. The reason that this is kept at 230 degrees is an issue, I believe, regarding the sulfur dew point within the process. So what they did was they went and installed an organic Rankine cycle onto that plant. So that takes in a hot water supply at 230 degrees and returns it at 220 degrees. And this plant produces in the order of 5 megawatts of electricity, which is then sold back to Anglo American Platinum. So just a short overview of, this is I think that's probably the cooling towers for the plant there, and this is the plant itself. Again, we're not talking about small pieces of equipment. The investment in this plant for 5 megawatt was in the order of 150 million rand, and it has a 17% efficiency. Plant lifespan in the order of 30 years. Probably the biggest challenge that there is to waste heat recovery is really the high variability in terms of temperatures and flow rates and even composition of the waste gases. So what you typically see in these kind of profiles is that you get significant and rapid variations in temperature. And when you put variations in temperature like that into a heat exchanger, it can often cause problems into the process. Even if your heat exchangers are fine, what you typically have if you're trying to drive a turbine off that is the turbine has an optimal design point. And if you're fluctuating the load factor all over the place, you really reduce the efficiency of your turbine. So this was some work that was done where they provided a small thermal storage system. And the thermal storage is not designed to store significant amounts of energy, but all it aims to do is smooth that profile slightly. And it really, I think it was only like 1 or 2 megawatt hours for this process, and they resulted in a 33% improvement in efficiency. So really thermal storage we believe has an important role to play in heat recovery. The one option is to smooth a variable supply, like I just talked about, but the other option is sitting when you have batch-wise processes. So how can you shift energy if you have a batch-wise process that is making waste heat, but you want to convert that into either flat profile, or even perhaps you would want to shift that to a different batch at a different time. So this is an R&D project that I'm currently involved in, looking at a ceramic manufacturer. So they produce engineering ceramics. These are 3 of their kilns, but they have some other kilns on the side of the plant. Essentially what they do is they fire alumina ceramics to the order of 1600 degrees. It's a batch-wise process, and then what happens is they spend in the order of 2 days cooling those kilns down, and they vent all that heat out the roof at the moment. On the other side of their plant, they're constantly casting from their molds, and they have a series of electric ovens that they're using to dry the moisture off of those molds. Part of the problem is that these molds are very sensitive. If for even a few seconds you start going above 60 degrees, they start to crack. And also, they cast almost all day in their production cycle, and they only fire sort of once a week, so there's a misalignment. So I must just say, as part of this, CSIR is really doing R&D on a thermal storage system for this, and NCPC have been kind enough to do a baseline energy audit for the company so we can really know what their savings are going to be. So what we are developing for this company is a thermochemical heat storage system. So if we start on the drying side, they will have a chamber where they can dry all their molds. What they do is they pass humid air through this drying chamber. We have a thermochemical material in there that essentially acts like a desiccant. It pulls the water vapor out of the air, and as part of that process, it also releases heat back to the air. So what we get is an efficient, extremely efficient drying system where we get hot, dry air. You also can't subject the molds to 0% humidity or they will crack as well. So we have to blend in some ambient air. But essentially what we do is we have an efficient drying process that eventually this bed will become completely waterlogged. It will absorb as much water vapor as it can. And then what we do is we use heat from the kiln to regenerate that bed. So we pass that to high temperature exhaust when a kiln is fired and they're cooling it down. We mix it with ambient air, drop it down to 200 degrees, and then we drive off all the water vapor that has been collected by that heat material. The advantage with this process is you can essentially store the heat recovered from your kiln indefinitely. If you're not passing humid air over this bed, there's no chemical reaction that takes place, and essentially your bed will stay at room temperature. So they really have the potential to store energy over months, even if they wanted to. Another option is that we get warm and humid air that will come out of here at 200 degrees, and we can actually look at condensing the water vapor from the casting process and looking at water recovery as well. So just very quickly to finish off, we're really in the beginning stages of the thermal laboratory. What we're really aiming to do is conduct really targeted R&D that is aiming to solve real questions that industry are asking. And how can we improve energy efficiency specifically within this thermal space, which is really where 70% of energy consumption is sitting in most industrial processes. So across the spectrum, we'll be looking at waste heat recovery. Power to heat is really a topic where we are looking at, in future, low-cost solar PV and wind are projected to become so cheap that at some point it actually makes sense to start electrifying loads. So instead of having a gas burner, you can use direct resistance heating to provide heat. You couple that with low-cost thermal storage, and that provides flexibility to the electricity grid as well as to your end-use customer. We're looking at solar thermal systems, particularly solar thermal for industrial process heat, and we're currently in the process of developing a plant at a recycling plant here in Johannesburg. Ambient heat, it's passive cooling design. So how can you transfer ambient cooling that is available in the evening periods? And then finally, so all of these are linked primarily with thermal storage to add flexibility to the energy system. So we're at a stage where we want to find out from industry what your problems are before we put all the hardware on the ground, and then start to really tackle those problems from an industry-wide perspective, not necessarily end use by end use, but at the end of the day, we're aiming to get hardware installed on the ground in South African factories. So roughly what a process would look like in terms of a lab development of a topic. If we take thermal energy storage, a significant part of that is materials research. So how do you optimize your storage materials? And then how do you get the heat in and out of your concept? Heat exchanger designs, heat transfer testing, and really prototyping and getting the equipment installed. So just to conclude, waste heat opportunities are really abundant, and I think I'd like to emphasize for people that are doing the energy audits to keep it in the back of your mind. Look at what are the energy streams, where is heat being exhausted to atmosphere. Even at temperatures in the order of 100 degrees, there's often something useful to do with that. It requires a lot more on the process side to understand the processes within a company. What is the flow of energy, doing things like pinch point analysis, finding out where the opportunities lie. But really, there is a big but here. It's not always a plug-and-play solution. It often requires detailed engineering work as well as extensive capital investments. But often the payback periods that we're seeing with these technologies are getting more and more attractive as the energy costs are rising. So there's a long road ahead, but there certainly is significant potential for this technology within South Africa. Thank you.